Hello, everyone, and welcome back. Now, if you think about what we've done over the course of this class, we started with just understanding the real number system. So this took us through sequences and open sets, the Heine-Borel theorem, all kinds of important results that help us to better understand the characteristics of the real numbers. And we use this understanding to then start talking about functions that transport real numbers back into real numbers, right? So you should always think of this as just a correspondence from one set to another set. That allowed us to talk about continuous functions, and then we pushed it even further to start talking about integrable functions. We saw that all continuous functions on a closed interval are themselves integrable, but the space of integrable functions is much larger. There are lots of functions that are not continuous that are still integrable. Now, that means that we have talked about integrals, that the natural sort of progression through a calculus-oriented course would mean that now we should talk about derivatives. And that's what we're going to do in the next few lectures. We're going to work to maybe re-understand the derivative, because this is typically what's introduced to you very early on in a calculus class. And the goal for today's lecture is to give you the basics of a derivative. So we remember that derivatives are posed in terms of this limit as h goes to 0. We're still going to have that. But we're also going to talk about a sort of abstract notion of differentials. Now, in the case of single variable calculus or single variable analysis, derivatives and differentials sort of mean the same thing, and it kind of is hard to parse what the point of learning differentials is. But as I'm going to try and explain to you, as we move further into more complex math and multivariable real analysis, even infinite dimensional real analysis, differentials are how you should really think about derivatives. So just bear with me. I'll give you the definitions as we move through. But like I said, the real goal today is to introduce the necessary definitions, and then we're going to give you the things that you probably already know about the derivative. We're going to prove them from first principles. So that's things like the product rule or the chain rule. And we're going to look at a few examples along the way. So let's go ahead. Let's jump right into it. So, of course, let's start with a definition. And this is probably the one that you already know. We're going to talk about what a derivative is. So the definition here. Now, we might have to brush up on some terminology from the section that we did on continuous functions, because we're going to say some point in the domain is a cluster point. Remember, cluster point means that we can get close to it without actually being at it. It's not an isolated point. So of the domain D sub f of a function f. So this is looking a lot like what we talked about with continuous functions. So we define now this is going to be the derivative of f at x0 to be, well, you know it, you love it, you've seen it many times probably, f prime of x0. This is the limit as h goes to 0 of f of x0 plus h minus f of x0 divided by h. We can probably write this in our sleep. We've seen it so many times. And of course, this is provided the limit exists. The limit exists. Now, I am hiding some machinery in the background here, right? If you think about what we did with our functions, and in particular continuous functions, we know that this limit has to be done in such a way so that x0 plus h remains in the domain, right? That's an important aspect here. That I'm just going to sort of tuck in the background, right? We've talked about this extensively. We use a lot of just closed intervals to talk about our functions. So we don't have to worry about that too much, but it is important. You should always think of a function as being a pair, the function and its domain. And we've seen the sort of nuances and intricacies that come with this, that come with different terms of domains. Now, alternatively, there's an equivalent way of writing this. We can write, say x is equal to x0 plus h, again, in the domain, and write the above limit as, well, you could just say that f prime of x0, this is equal to the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0. And it's probably this limit that we use to really understand what the derivative is in an introductory calculus class, because this is really rise over run, which we remember maybe from our introductory functions classes. This is really just a slope. And so this is something that we take with us, especially through single variable calculus, is that what we are doing when we compute the derivative of a function is finding the slope of the tangent line at that value. And the derivative function is just a whole function that returns to you slopes. So you give it a value, say x, it gives you f prime of x, which represents the slope of the tangent of the function f at the point x. All right, so there's lots of information encoded just by writing f prime of x. Okay, so let's look at some examples. These ones are probably not going to be too revelatory to you, but I just want to explain, how we can actually use these limits in practice. So let's let f of x equal to the absolute value of x. So we claim that f prime of 0 does not exist. So it does not exist. So this thing has no derivative at 0. Now, you probably already know this, right? We know that the absolute value function is this very sharp v, and we know that those sharp corners, maybe, they represent places where you're not differentiable. So you sort of can't round your way around these things with a tangent line. Now, how do you do this in practice? Well, you would say the limit as h goes to 0 of 0 plus h, right? Because my x0 is equal to 0 here, minus the absolute value of 0 divided by h. Well, this is the limit as h goes to 0 of the absolute value of h divided by h. But if we take the taking h going to 0 from the right implies that the absolute value of h is just equal to h, which tells me that the limit as h goes to 0 of the absolute value of h over h, well, this must be just 1. So that's telling me the slope of the tangent line as I approach from positive values of h is looking like it's going to be 1. On the other hand, if we take h going to 0 from the left, so approaching from the negative side, then I get the absolute value of h is equal to minus h, which tells me that the limit as h goes to 0 of the absolute value of h over h is equal to minus 1. And this tells us now that depending on which side we approach from, we get different limits, and therefore the limit does not exist. So therefore, limit as h goes to 0 of the absolute value of h over h does not exist. And that tells you that your derivative does not exist there either. All right, so this is probably a very common example that's used throughout introductory calculus, but it's nice to recall it. Now, let's look at the same example, but let's show that the derivative exists elsewhere. So again, let's take f of x equal to the absolute value of x and show f prime of x0 is equal to 1 for any x0 greater than 0. So if you want to do this for a negative value of x0, you show that the slope is equal to minus 1. We're just going to do it for positive values just for the sake of illustration. Well, first of all, we can take, since we're considering a limit here, we can take h such that the absolute value of h is less than x0. Remember, this is sort of your delta component. X0 is positive. It can function like your delta in your limits. And so we can see that the limit here as h goes to 0, well, let's write it out. This is x0 plus h minus the absolute value of x0 divided by h. That's just f of x0 plus h minus f of x0 divided by h, right? It's your usual quotient for the derivative, blah, blah, blah. Well, since the absolute value of h is less than x0, that tells us that x0 plus h, maybe I'll just circle it so you can see what I'm looking at. This thing is greater than 0. Right? Because h can't stretch all the way into the negative values when you're adding x0 into it. So that means that since x0 is positive and x0 plus h is positive, the numerator here is just h, the denominator here is just h, and this is equal to 1, which by definition is equal to the derivative at x0. So nothing fancy, but it's nice to see how this works, especially now that we have a very, very good understanding of how to take these limits, because we spent all that time doing limits of functions when we were talking about continuity of these functions. Let's do the last one. Let's talk about polynomials. Okay, so let's let f of x equal to x to the n, where n is some natural number. Okay, let's compute the derivative of this thing anywhere. So I'm going to do f prime of x. So I want to know what the sort of derivative function is. We'll talk more about the actual derivative function later. So you can think about x just being fixed for now. Well, I'm taking the limit as x goes to 0 of x plus h to the n minus x to the n divided by h. Now, you might need to brush up on some ideas here, because this is going to use the binomial theorem to expand this out. So I take the limit as h goes to 0 of 1 over h. Let's pull out that h denominator. And now I get x to the n, and then plus n times x to the minus x n to the minus 1 times h plus n times n minus 1 over 2 x to the n minus 2 h squared. And there's so many terms in here, right? This is just the binomial theorem that allows me to expand this out. But the important point is, first of all, the xn's or x to the power of n cancels. And you can see that this 1 over h cancels that h there, cancels the square, brings this down to n minus 1. And so you can see that the only term without an h in it is that n times x to the n minus 1. Everything else disappears in the limit, which gives you n to the x to the n minus 1. Okay, I said that was the last example, but I actually have one more, and I'm going to leave it for you as a super, super simple exercise. But if f of x is equal to c, a constant, well, we've seen this a million times, right? Then f prime of x is equal to 0 for all x. Okay, so what I want to emphasize now is that technically I haven't done anything with a sort of slope of a tangent, right? So all that I've said is that the derivative, by definition, absent of any physical understanding, is just equal to this limit. Now, we learn the physical understanding very early on in the calculus class. You learn that it is the slope of a tangent line. So if I can offer up a little sketch here for a second, let's see what's happening. We've seen this before. It's sort of the limit of the secant associated to the function. So let's imagine we've got a function. Let's just say it looks like this. Just a really, really sort of poor little sketch here. But I've got, let's say this is f of x, and this, I'm going to imagine I'm really, really zoomed in here so that this actually makes sense and so that h is small. But this is f of x plus h. And we've got this secant line that connects these things. And so we know, let's just put this in, the slope is equal to f of x plus h minus f of x divided by h. So what we could do alternatively is we could define, say, the change in f, right? So this might be a sort of more physics-based notation. This is f of x plus h minus f of x, and this is sort of for a fixed h. Now, basically what we want to say is that when h is really, really small, this thing is basically a linear function of h. So this might be m times h, where m is the slope. That is your sort of intuitive understanding of how we talk about the derivative in terms of the slope of a tangent line. We're saying that when h is really, really small, then this difference here looks a lot like just a linear function. And you can really, really see it based on my my sketch here. You know, as this dot, the rightmost dot, gets closer in to the leftmost dot, this thing is looking, the function is looking a lot more like just a solid line, right? So you're sort of zooming way, way into the function, starting to look more like a line. This is the sort of more natural way of thinking about derivatives, especially as you get up into more abstract mathematics or higher dimensional functions. And so this is going to lead to the idea of what's called differentiable. So we say the function f is called, in our case, differentiable. So this is sort of more macroscopic than just taking the derivative. So it's differentiable at a cluster point pt for point x0, provided that there exists a linear function, right? So we know what a linear function is. Y equals to mx plus b. In our case, it's going to be this L of h is equal to mh. So there's no y-intercept, such that, sorry, it should, I was saying b, this should be mh, pardon me, just like I have it above, such that the function given by, well, here we're going to have epsilon of h is equal to this delta f that I have described above minus L of h divided by h goes to 0 as h goes to 0. So you can think of epsilon here as describing the error. So I don't want you to get confused with the previous epsilons that we've used. But what I do want you to see here is that when you multiply up the h, look what happens. This, so let's just put a remark on the next slide. Well, this implies that delta f is equal to L of h plus epsilon of h times h. And if I unpack my delta f, this is really saying f of x plus h is equal to f of x plus, now I'll unpack my L of h, that's m times h, plus epsilon of h times h. Now this should look very, very familiar to you because this is essentially a very primitive version of Taylor's theorem, right? This is expanding just up to linear order. This is your Taylor remainder. So we are going to get to Taylor's theorem as we progress through these videos, but I just want you to see that this idea of being differentiable is very intimately related to Taylor's theorem. And you can think of epsilon as capturing the error or the remainder from Taylor's theorem. Okay, so let me give you a nice theorem. And of course, it's going to tell us that the notion of derivative and differentiable are exactly the same thing. So a function f is differentiable at a cluster point. So we always need the cluster point here. x0, that of course belongs to the domain, or else this wouldn't make sense. If and only if f prime of x0 exists. Now we know what it means for that to exist. That means that the proper limit definition of the derivative exists. And furthermore, if f is differentiable, I'm going to use DIFF to denote differentiable. It's a long word. It offers a massive opportunity for me to misspell it. So I'm going to say DIFF for differentiable at x0. Then, of course, your linear function L of h, well, that slope has to be f prime of x0 times h. And this is denoted by, we write, so again, this is sort of getting us into a little bit more abstract mathematics, df sub x0 of h. So the d stands for derivative, f is the function you're considering, x0 is the point you're at, and of course h is your sort of moving around x0. And delta f is equal to f of x0 plus h minus f of x0. We've already seen that part. And from the differentiable, or from the differentiable definition, we know that this thing has to look like this. And of course, where epsilon of h goes to 0 as h goes to 0. And of course, that h going to 0 in such a way so that, x0 plus h is actually in the domain. We always have that sort of coded language in the background. It's just a pain to write every time, and you should already sort of have this intuition built. But what did I do here? Again, all I'm doing is proving a very, very basic version of Taylor's theorem. I'm relating the idea of the derivative from that limit, from the definition at the beginning of this lecture, to differentiable, which therefore gives me this sort of basic version of Taylor's theorem. Okay, so this is an if and only if proof. That means I'm going in two different directions. So let's go from left to right to start. And we suppose f is differentiable at x0. We want to show that the limit exists, and we want to show that we have this correspondence between the slope and x0 from our differentiable definition. So then there exists some m and r such that, well, from the definition of differentiable, the epsilon term, the error term, delta f minus m times h over h goes to 0 as h goes to 0. Just the definition of differentiable. And so thus, well, remember delta f over h, that is the limit that we're taking for the derivative. So of course, this is f of x0 plus h minus f of x0. Divide that whole thing by h. Well, from my epsilon term above, my sort of Taylor's theorem that I've been talking about, this is equal to m plus epsilon of h, which goes to m as h goes to 0 by definition of that epsilon. So therefore, f prime of x0 is equal to m. And by proxy, because it has a value, it exists. All right, so let's go in the other direction. Let's assume, so we suppose f prime of x0 exists, and we know that this is coded language for saying that that limit actually exists. Let's say let m equal to f prime of x0. Remember, for the definition of differentiable, we need to identify what that value of m is so that we have our linear function. And let's define L of h equal to mh. So that's my linear function. That's my candidate for my differentiable definition. Now let's move to the next page here. Let's let epsilon of h equal to delta f minus L of h over h. So again, I'm defining these things in order to give me the definition of differentiable. This, by definition, is equal to, so I'm going to unpack this whole thing, f of x0 plus h minus f of x0 divided by h. And L of h, that's m over h, which is the same as f prime of x0, because the h's will cancel. But we know that because the derivative exists, this first quotient approaches f prime of x0. The other piece doesn't depend on h, so it is just f prime of x0, which is clearly equal to 0, which implies that epsilon of h approaches 0 as h goes to 0, which shows f is differentiable at x0. And that gives us our proof, right? So again, really all we're doing is we're sort of uniting the sort of strict mathematical definition of the derivative, that's the limit definition that we started with this sort of more geometric intuition coming from the differentiable definition, and in particular, this sort of Taylor's theorem that we just talked about here. So I know it's not too revelatory, but again, it's this differentiable definition that really tells us how we can understand derivatives as we have more variables, and in particular, as we move to, say, infinite dimensional vector spaces that you might do in a later class. The other thing is that this notion of differentiability actually affords us a lot of leeway. It makes things a lot easier when we want to talk about properties of functions that have derivatives. So let me give you an example of that. I have a nice corollary. If f is differentiable at x0, then f is continuous at x0. Okay, so again, this is something that we knew, right? The only way that you can be differentiable is you have to also be continuous. Discontinuous functions are not differentiable. So how do we prove this? Well, we're going to use that differentiable definition. So remember, to be continuous, we need to prove, that the limit as x goes to x0 of f of x is equal to f of x0. Now, again, I'm using the sort of shorthand limit notation. You know that this sort of can be framed in terms of epsilons and deltas, but now that you understand it, I'm going to use this shorthand as we go through. This is equivalent to proving, well, this is the same as asking yourself if the limit as x goes to x0 of f of x minus f of x0 is equal to 0. This is the same idea that we talked about with sort of null sequences way back when we talked about sequences. Well, then let's denote h equal to x minus x0. So where you want to go, x0, where you are, h is just telling you how close to x0 you are. And we have, well, we're going to use that notion of differentiable. So we're going to say the limit as h goes to 0, which is the same as x going to x0, of f of x0 plus h minus f of x0. So that is this limit right here that I care about. Remember from the original definition at the beginning of class with the beginning of this lecture with the derivative, right? I can equivalently pose it with h going to 0 or x going to x0. We know, we've seen it before. Well, this is the same as the limit of h going to 0 of, now let's take a look at this. Let's use our differential notation now, df of x0 of h plus epsilon of h times h. And we have that this thing is equal to the, let's use the proper definition. This is f prime of x0 plus epsilon of h. I'll factor out an h here because that h that's been factored out is going to sink everything and gives me that this is equal to 0, which if you trace it all the way back up, that tells you f of x0 plus h is approaching f of x0. Gives us exactly what we want, tells us we've got our nice continuity here. Okay, So what I'm going to do is I'm going to give you the usual derivative rules that you've seen many times. And I'm not going to prove this theorem because I think that the theorem, it's typically proved in sort of introductory calculus classes. It's a fairly straightforward theorem to prove. And I want to leave it for you as an exercise to see if you can really grasp the definition of a derivative and maybe see if you can use differentials as opposed to using that limit from the derivative notation here. So let's say, suppose f prime of x and g prime of x both exist. Okay, so I can take derivatives of these functions. Well, then I'm going to give you a sort of list of all of the things that you've seen a million times. Well, first of all, if I add or subtract these functions and I take a derivative, well, this is the same. This is the same as saying this exists and f plus or minus. So this derivative itself is just the sum or difference of the original derivatives. So this shows us that the derivative distributes over sums and differences. Next, we'll do the product rule. So if I take the functions f and g and multiply them together, and then I take a derivative, well, of course, this exists. And this derivative is equal to, well, f prime of x, g of x, plus f of x, g prime of x. This is your usual product rule. And let's close it off with the quotient rule. So if I take the quotient of f and g, well, this thing exists and its derivative. So this, well, you might remember this one. This is f prime of x, g of x. Usually this is the one most people have trouble remembering. But here it is, f of x all squared. But there is an important nuance here, right? Of course, you need to know that the value of x is actually in your domain. So if x is actually in the domain of the quotient of the function, f over g, and it is a cluster point. So this one comes with a little more nuance, but it's not really anything revelatory or that new for us. So like I said, we've seen these all a bunch of times. I'm going to leave them as an exercise to see if you can work them out yourself. But what I'm going to do is you'll notice, of course, I left one derivative rule out, and that's typically the most complicated one. That's the chain rule. So what I'm going to do is I'm going to present the chain rule as its own theorem, and we're going to actually work through and show how differentials can be used to prove the chain rule. Okay, so chain rule here. Well, let's take a look at this. Remember, suppose g is differentiable at x0 and f is differentiable at g of x0. Right? So remember, we're talking about compositions for the chain rule. So then f of g, the composition, the derivative at x0, well, this thing exists, and the derivative of the composition, this one again is one that people have a lot of trouble remembering. So see if you can pause the video and remember exactly what this says. But this gives me f prime of g of x0 times g prime of x0. Okay, so this is the sort of Russian doll one, right? The derivative derivative of g comes outside of this composition. So how are we going to prove this? Well, we're going to use the definition of differentiability. So let us begin. So let us denote, I'm going to denote k. And now k is actually a function of h. This is going to be that delta g. So this is going to be g of x0 plus h minus g of x0. And since we know that if you're differentiable, which we assumed, then you must also be continuous, this thing goes to 0 as h goes to 0. And that's since g is continuous at x0. All right, so we already proved that. Also, from the fact that you're differentiable, k, which is equal to delta g, well, we can use that, that sort of rudimentary or the basic version of Taylor's theorem here, which tells me this is equal to g prime of x0 times h. That's my linear part. And then plus, I'm going to call this epsilon tilde, because we're going to have another epsilon that comes in for the function f. So that's my error term for the linear approximation for the g function. And of course, by definition, we know that epsilon tilde of h goes to 0 as h itself goes to 0. This is just from the definition of differentiability. So all we use is so far is the fact that g has to be continuous. And so k goes to 0 as h goes to 0. And we use the definition of differentiability. So next, we can form the quotient that we desire to show that f of g is differentiable or it has a derivative, right? So then let's look at this. This is just the basic setup of what we care about in terms of differentiability. Sorry, g of x0. Divided by h. So we want to show that this thing actually approaches f prime of g of x0 times g of x0 as h goes to 0. Okay, so the first thing that we're going to do is we're going to use the fact that g of x0 plus h, we can, let me underline it so everyone can see it. This thing right here, we can rearrange. And so this becomes f of g of x0 plus k, and that's really k of h, but I'm just trying to minimize some notation here, times f of g of x0 divided by h. But now h is differentiable, right? So what you can see is that g of x0 is the point where you're differentiating around. K is going to 0. So the top of this thing is a delta f function. And so from the definition of differentiability, let me pull this equal sign over just a little bit to make some more room for myself. This becomes f prime of g of x0. That's the m term, your differential value, times k plus epsilon of k times k. That's just using the fact that h is different or f is differentiable at g of x0. Okay, so be careful. The notation makes it look way more complicated than it actually is. If you want to make this easier on yourself, introduce y is equal to g of x0. That might help simplify some of the notation here. Okay, nonetheless, now I've got the top in terms of k's and the bottom in terms of h's. Now we know k is a function of h. Let's unpack it. Let's open it up. We know that k is equal to, so let me write this out. Well, k is g prime of x0 times h plus epsilon tilde of h times h. And then this is all over h. I'm going to distribute this over a sum, mostly because I've sort of run out of room going to the right. So then this becomes plus epsilon of k, and then the same thing, epsilon tilde of h times h, all divided by h. Now let's just sort of take a look at what happens here. This h right here and this h are going to cancel. And so then taking the limit as h goes to 0, well, there's no h dependence in the first term, so that gives me g of x0 times g prime of x0. So that's the piece that I want. Then if I look at this h right here that I circled is going to cancel with the quotient, but this part is going to 0, this epsilon tilde of h. Similarly, epsilon k is going to 0. So this, and this may cancel, but the epsilon of k is still syncing everything, telling us that we just wind up with exactly what we wanted. That this derivative here is actually equal to f prime of g of x0 times g prime of x0 as h goes to 0. And therefore, we have shown that the derivative of that value exists. And from our equivalence between the derivative and being differentiable, that tells us that the composition is differentiable at x0. Okay, so we did it, right? We introduced derivatives, but we also introduced a sort of more abstract version, and that is differentials. Now, what is really, really great for us is that these are the same thing. You're just looking at it in two different ways. And I really want you to keep that perspective in mind. The derivative, you always think as being that sort of slope, right? Rise over run as h goes to 0. Whereas this notion of differentiable is much closer to Taylor's theorem. Actually, it is in fact Taylor's theorem, just up to the linear order. And so these are two different perspectives that you can take. I like to think of Taylor's theorem as zooming in on a function, and you are zooming in and in and in and in and in. And in our case, we're zooming in so much that it just looks like a little tiny line. That's what that linear approximation looks like or is doing. Now, the nice thing about this differentiable definition is it makes some of our proofs a lot easier than having to do the old school or rudimentary version of taking that limit to find the derivative. And we saw this in particular in the last proof with the chain rule. The proof of the chain rule with usual definitions of derivatives is a huge pain. Whereas here with this definition of differentiable and this Taylor's theorem perspective makes things a little easier to manage.